Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Hey everyone, Sam again with another quick TWIMLCon update. One of the things that's been especially exciting to see is the number of organizations sending multiple people, in some cases entire teams, to TWIMLCon to learn about scaling and operationalizing machine learning. A full third of the companies attending are sending groups, in many cases 3, 4, and 5 people. This is awesome. Seeing so many teams attending is a great indicator that folks really see the opportunity associated with improving the efficiency of their data science and machine learning operations, and are excited about the conversations we'll be curating at the event. If you'd like to attend TWIMLCon with your team, just reach out to me at sam@twimlai.com and let's make it happen. Of course, you're welcome to reach out to me if you want to attend as an individual, or just head over to twimlcon.com/register to sign up. All right, on to today's show. All right, everyone, I am on the line with Anubhav Jain. Anubhav is a staff scientist and chemist at Lawrence Berkeley National Lab, as well as the group lead for the Hacking Materials Research Group. Anubhav, welcome to This Week in Machine Learning and AI.
Yeah, it's great to be here. I've actually learned a lot by listening to your podcast, so it's really exciting to be able to share my work with your listeners as well.
That is fantastic to hear. So the group you lead is called the Hacking Materials Research Group. That is such a compelling name. Tell us a little bit more about your kind of focus and charter and what you're trying to accomplish.
Yeah, so what we're really trying to do with the research group is to apply computing to accelerate the process of finding new materials for functional applications. So new chemical compositions or new crystal structures that have really interesting properties. And these days, it's actually possible to use computer simulations and also data mining to really change the way that process is being done. So my group works both on theoretical methods to predict materials properties, and it also works on data mining and machine learning techniques to help accelerate materials design.
Awesome. And so what led you to combining computing and machine learning and materials? What was your path?
Yeah, so I got into material science because I really liked kind of its central premise, which is that, everything, whether it's an airplane or a computer processor or a battery, it's all made of materials. And the properties of those materials really determine the fundamental limits on the performance of every device. And, many people have pointed out that, whenever there's a fundamental materials advance, we often name like an entire historical era after it, the Stone Age, the Iron Age, the Age of Plastics, or the Silicon Age. Huh. And so, I've really been interested in, how can we actually...
I hadn't heard that before. That sounds amazing.
Yeah,
it really underscores the importance of materials and the opportunity that's available now that we're kind of applying machine learning and data science to the field.
Yeah, and there's all sorts of new applications like quantum computing you might have heard of, or new biological technologies that really require materials advancements as well. Mm-hmm. But now, typically material science has been very data poor because the only way conventionally to get information about materials was to perform an experiment. That means you have to synthesize the material, put it in a machine, and it might be like $10,000 per data point that you're collecting. And so the way that I got into this field is that during my PhD, I worked with someone named Gerhard Sater, who was at MIT at the time. He's now at Lawrence Berkeley Lab, like I am. But what we were doing was we were using a particular type of computer simulation that's rooted in quantum mechanics. And then we would use these simulations to actually predict the properties of materials, do kind of a virtual measurement in the computer. And we could do this for maybe like $1 to $10 in computing costs per material. We could scale that over computing clusters so it was easy to parallelize. And then it was easy to create these databases of materials properties based on simulation data. So now we had a way to actually generate large materials data sets, and maybe even too large materials data sets where conventional analyses were difficult to actually figure out what were the trends in that data. So I got into data science and machine learning after generating some of these large databases of simulated materials properties as a way to kind of figure out what more information we could extract from some of that materials data.
Yeah, that's an interesting trend that I talk to folks about kind of across different domains. The integration of the use of simulated data and machine learning. I think one of the most recent conversations on this topic was in the area of astronomy, if I'm remembering correctly. Talk to me a little bit more about how you are combining that simulated data and machine learning.
Yeah, so typically the way that it's done now is in a kind of a tiered screening process for new materials. So when you have an idea about a new materials or a new chemical space that might be used for a functional application, you might first do a machine learning prediction, and that machine learning might be trained on simulated data because there usually isn't enough experimental data to train on. So you first do like a machine learning prediction to see what might be the interesting materials candidates within this broad chemical space. Then you might run some simulations on the things that are interesting for machine learning. The simulations are a little bit more expensive and complicated and time consuming to do. And then finally, if it passes both of those tests, you can actually do experiments. You might want to actually target doing some real experiments on that material. So that's one paradigm in which the techniques are working together. There's also kind of active learning and adaptive design type frameworks where you do this whole thing in a loop. So you do iterative machine learning, and based on the results of the experiments, you retrain your machine learning model, run the computations, and do this whole thing in a loop as well. So there's a few different kind of paradigms in which you can mix these different techniques.
Do you apply different types of domain adaptation techniques when you're trying to use the simulated data in the materials domain? Is that a technique that's effective in the kind of work you're doing?
Yeah, so I'm actually unfamiliar with the term domain adaptation technique. What does that refer to?
I guess, it's similar in some ways to data augmentation. It's really, take, for example, in autonomous vehicles, one of the things that you hear people doing is training on different types of simulations like video games, but the models that are trained in these simulated environments don't generalize well to the real world. So they'll do different types of things to adapt or modify the simulation to help the model generalize or perform. So for example, they might, take daylight scenes and turn them into nighttime scenes or manipulate them so they seem more realistic. I'm wondering if there are any kinds of tools or techniques that you apply to make models trained on simulated data rather more applicable to the real world interactions.
Yeah, so I would say there's two parallel threads, none of which is maybe exactly what you're mentioning here. One of them is just kind of rooted in physics and trying to make the models as realistic as possible by improving the underlying physics of those models. So try to just get them to be closer and closer to reality. The second kind of approach that's taken that's somewhat similar is kind of a multi-fidelity approach, where you have some experimental data, you have a whole bunch of computational data, and then you maybe use some of the computational predictions as features to help train your experimental model, your model trained mainly on experimental data. So I think those sorts of approaches exist, but I haven't seen any sort of systematic transformation between computational data and kind of real world results other than those sorts of examples.
Oh, really interesting stuff. Now, I probably should have mentioned this earlier. We're primarily going to be focused not necessarily on some of the materials applications of machine learning that you're working on, but rather some work that you recently published on applying natural language processing to capturing information from academic literature. So maybe if you can talk a little bit about that work and its motivations and the connection between it and what you're doing on the material side.
Yeah, so, there are many, many millions, probably 50 to 100 million research articles, scientific research articles that have been published. And there's probably been trillions of dollars of investment in actually funding the research studies that typically the only output of those research studies is a published research article. So there's a ton of knowledge and a ton of opportunity in terms of extracting information from published research articles. And today, it's kind of crazy, but the main way to actually get information from research articles is to have, researchers read them. And that process is really, limited. I mean, as a researcher, I probably read a few dozen articles, like really read a few dozen articles per year. Maybe for some people it's a few hundred, but there are thousands of articles published on any domain at any in any given year. So what we were trying to do in our study was to design some kind of a system that would be able to, let's say, read these articles in some sense and synthesize information about what those articles were saying, and be able to conceptualize, what was happening in material science by reading these articles, and not only be able to have these internal conceptions of what the articles were talking about, but to make predictions that could be testable and help guide researchers in their studies. And so in this paper, what we did was we actually collected the abstracts of over 3 million articles restricted to material science. We did some data pre-processing on those articles. And then we actually trained an unsupervised algorithm called Tyvek. So this algorithm didn't receive any label data. It didn't receive any chemical training. But we found that by applying this algorithm on just the data set of material science articles, it was able to conceptualize concepts like the periodic table. And it could also predict what materials should be studied for functional applications. We found that through this procedure, we were able to predict materials that should be studied for various applications many years before they were actually reported in the literature. So we did this process where we actually kind of virtually went back in time, made some predictions about what material scientists should be studying, what materials they should be studying for different applications. And then we saw, in reality, did they actually study those materials that we predicted over the next few years. And we found that, we could actually predict at a very high rate what researchers would be studying in the future.
Well, if we can pause here and maybe unpack some of that. I think probably many listeners are generally familiar with Tyvek and the concept of word embeddings. We've covered it quite a bit on the podcast. But you say that in creating an embedding model, you're able to, the model is able to conceptualize the periodic table. What does that mean for a model to be able to conceptualize the periodic table, or what are you trying to express with that?
Yeah, so, as you mentioned, there's been a lot of research into Tyvek, and people have already demonstrated many times that it can, understand grammatical relationships. It can also understand semantic relationships like the concept of gender or capitals, etc. What we're trying to show with this study is that Tyvek also captures scientific relationships. So it actually captures knowledge that requires some amount of scientific knowledge in order to express that relationship. So for the periodic table specifically, what we did is we trained these word embeddings, and then we looked at word embeddings of the chemical elements. So words like helium, words like sodium, words like lithium. And so these are 200-dimensional vectors that represent these words. And then we projected those 200-dimensional embeddings into 2 dimensions, like the periodic table. We used t-SNE as the embedding mechanism, as the projection mechanism. And then we found that when we actually projected these word embeddings, which were trained just on the way that chemists and material scientists mention these elements in the course of their research, we actually got the same sorts of trends that you saw in the periodic table. So without really being explicitly trained on what the structure of the periodic table was, we could recover that structure simply by reading these articles and projecting these embeddings down to 2 dimensions.
And just to interrupt again, when you say recover that structure, meaning if you somehow visualize this 2-dimensional embedding space and squint the right way, you can kind of see the periodic table in there, or you can systematically, further transform this projection and get to something very close to the periodic table. Yeah,
so we did kind of two types of tests. The first one is more similar to what you described at first, which is that when you project the elements in 2 dimensions, you kind of see these clusters that correspond to the types of groups in the periodic table. So things like the alkali metals are all grouped together, the halogens are all grouped together, et cetera. Mm-hmm. And there's also structure within the clusters that you can see that correspond to moving to certain directions in the periodic table. But now, you're I think you've talked on the show before about how t-SNE can distort things and distort distances, et cetera. And so in addition to kind of just that t-SNE visualization and qualitatively looking at it, we did another thing, which is we actually first took these 200-dimensional word embeddings and projected them down to 15 dimensions using just PCA. And then we saw whether certain directions in that 15-dimensional embedding space corresponded to various directions in the periodic table. So for example, we saw whether there were certain directions in this 15-dimensional space that corresponded to increasing the atomic weight in the periodic table, or increasing the electronegativity in the periodic table. So what we were really doing is to see, are there certain directions in this embedding space that correspond to moving in certain directions in the periodic table? And we've found high correspondence in that as well, things like R-squared values of about 0.8 or so. So we also did a more quantitative test of whether the information in the periodic table was being captured by these embeddings.
Oh, really interesting. And now, can you take a moment to kind of review or overview t-SNE and PCA for those that aren't familiar with those terms and kind of how they play out in these experiments?
Yeah, so t-SNE stands for t-stochastic neighbor embedding. It's just a way to take a high-dimensional space like the 200-dimensional word embeddings we've been talking about and project them into a lower dimension in a way that tries to preserve distances as closely as possible. And PCA stands for principal component analysis, and it's a way to try and figure out kind of new direction, so new dimensions along which to project our 200-dimensional vectors that try to capture as much information as possible while reducing the number of dimensions down. So in this case, in order to test whether we were quantitatively reproducing the periodic table, because there's only 100 elements and there's 200 dimensions in our word embeddings, to do the test fairly to see whether we were capturing these directions properly, we actually reduced the dimensionality down to 15 dimensions to make a fair test.
Awesome. And so you created this embedding space, you kind of compared it to your intuition and knowledge of chemistry and physics and found that, there is some structure there that resembles what we know about the way the world works, i.e. the periodic table. And then, with this as a basis, you're using it to try to predict materials that will be useful in further research and literature. How do you make that jump from the embedding space to these kinds of predictions?
Yeah, so when you train these embeddings, you typically give it some kind of a task in which you train the embeddings on. So in the case of Word2Vec, the task that you train the embeddings on, there's multiple versions, but we use something called skipgram. And the task there is that given a certain word, that word could be a chemical element like helium, it could be an application word like thermoelectric, or it could be just any old word. Given a word as an input, the skipgram model tries to predict what words will appear next to that word in your document corpus. We use a window size of 8, so plus or minus 8 words from our target word. So what we're training these embeddings on, the information that they represent, is what are the neighbors, what are the types of neighboring words that occur next to each target word. So now we have basically for every word in our corpus, an embedding that represents what sorts of words are expected to appear next to that word in a scientific abstract, in a material science abstract. Now, the way that we make this predictive is a lot of times when people train Word2Vec or similar embedding algorithms, once they get the embeddings, they throw away the task. The task is not really important anymore. You have the embeddings and then you work with those. What really the lead author of this paper did, his name is Vahe Chitoyan, he decided not to throw away the task and he decided to use that task directly. And what he said is, well, listen, I want a thermoelectric material. I have a model that can predict what sorts of words are likely to appear in a scientific abstract next to the word thermoelectric. That's directly my Word2Vec model. So let me use my Word2Vec model to actually directly predict, in some sense, what words will appear next to the word thermoelectric. And then he filtered those down to just chemical composition words. So which chemical compositions will likely appear next to the word thermoelectric. And most of those chemical compositions predicted by the model are things that were already known to be thermoelectric, so things that occurred in our corpus many, many times. But then when Vahe got down to, let's say, the 333rd prediction, he found something new. He said, okay, here's a chemical composition that was never explicitly mentioned in our corpus as a thermoelectric, yet it's ranking pretty high in the prediction of likely to appear next to the word thermoelectric. So maybe the model is telling us something. It's telling us that there's a high likelihood that someone's going to publish a research article with this chemical composition next to the word thermoelectric, even though no one has ever published that article before. So he essentially turned the word Tyvek into a way to identify gaps in the research literature by using these embeddings.
And now, how do you validate your interpretation of a finding like that? I'm imagining that that 331st could be maybe it's a chemical compound that has another name or another kind of composition and has appeared, but under this other name, or maybe it's just random. Like, how do you validate that this is actually a function of the model that you've created and not just noise?
Sure. Yeah. So I should first say that we're pretty confident that the materials that we predict as new predictions are actually things that haven't been studied before. Because first of all, we can check our abstract corpus to make sure that that compound has not appeared next to the word thermoelectric or any other word that would indicate studying that application before. So part of it is using our corpus to figure out that this hasn't been studied before. And then we also did a lot of manual checking whenever we published a prediction in the paper, just to make sure that this chemical composition that we're predicting is not actually something that has been studied. So I think we're pretty confident that it's actually a new prediction. But then whether it's correct or not is, I think, a more complicated question. The best validation would be to actually do the experiments. So to make the material, to characterize it, and then measure the thermoelectric properties, let's say.
Sure. Yeah, that sounds expensive.
Yeah, so we're working with collaborators right now on a couple of those top 50 materials that we predicted in our paper. But it will probably be like 6 months or so before we actually find out what the results are. Just because they have to first synthesize the material, they have to purify it, they have to characterize it, and they have to optimize and dope it and all that stuff. So it's going to take a few months to figure out whether the ones that we picked out of the 50 are actually interesting or not.
I mean, I imagine it's even interesting if the model can come up with plausible candidates, even if they don't ultimately work. I mean, that's what scientists do. I guess I'm trying to get at a more kind of technical validation that, it's not just kind of random. You're finding these, plausible predictions more consistently than, just any combinations of molecules that appear in, that can be made up from the embedding space. Does that question make sense?
Yeah. So absolutely. And so in the absence of experiments, we actually did 3 types of alternate validation. So I think experiments would be the best, most, you can't argue with it type validation. But then in the absence of experiments, we did 3 other types of validation. The first type of validation we did is that we had an independent data set of simulated data on thermoelectrics. So these are based on, physics-based simulations. So the 2 data sets between NLP and the simulations, they don't talk to each other. And then what we did was we looked at correspondence between the ranking of thermoelectrics that we did using natural language processing technique and the thermoelectric properties as calculated by the simulated data. And what we found is pretty remarkable, which is that if you look at, for example, the top 10 materials in the NLP rankings, a lot of them are like the 99th percentile, 99.5th percentile, et cetera, of the actual simulated data properties. So there's a high correspondence between the word Tyvek rankings, the NLP rankings, and the simulated data. And that's not only on known materials where you would expect that the word Tyvek would pick up that it's a known thermoelectric, so I'm going to rank it highly, but also on unknown materials. So we have simulated data on the predicted data, and the things that we predict to be high with NLP are also high in the simulations for predictions. So that's kind of one validation, is just consistency between simulations and the NLP. The second type of test that we did was against experimental data. And here, what we tried to do is to say, because experimental data would be all on known thermoelectric materials, we actually tried to make sure that the quality of the ranking also corresponded to the quality of the experimental results, so the quality of the ranking and the experimental results. So things that had a higher word-to-vec ranking would also have a higher experimental-based ranking. And so that second validation also panned out, where there was kind of a rank correlation between our NLP results and between the actual experimental data. And then finally, the third type of validation that we did was basically a forecasting-based cross-validation. And what we did is we created these virtual data sets where we asked the question, well, what if we had invented this technique back in the year 2000? So we threw out all the data of abstracts from past the year 2000, and we trained the model only in the year 2000, for example, on data up to the year 2000. And then we made predictions at a particular point in time. And then we saw what actually happened in the research community in the next 19 years, from 2001 to 2019. Did those predictions that we made using the 2000 data set actually pan out over the next 19 years? And we repeated this process for every year from the year 2000 to 2018 or so, where every year we kind of virtually predicted what the algorithm would have predicted, and then compared that to what was actually observed in the research literature. And we found that the rate at which the materials that were predicted by the algorithm were actually reported in the literature was much, much higher than if you had just picked random materials from the data set at the time, and even more than if you had used some kind of chemical heuristics and simulation-based heuristics to pick the materials from at the time. So something like, within the first 5 years, you're like 8 times more likely to get a thermoelectric material using this algorithm versus just picking a random material. So that was like a third type of validation we did. And we found through that type of validation that often you could find new thermoelectric materials or suggest new thermoelectric materials 5 to 10 years before they were first reported in the literature.
Oh, that's super interesting. So, but it sounds like you did find that the algorithm was, the predictions that the algorithm came up with tended to be kind of like low-hanging fruit in the sense that they were found, within they tended to be found within the first 5 years, as opposed to, something that I guess I wouldn't expect this of an algorithm to come up with truly novel compositions, things that took 20 years to figure out. Is that basically in line with what you saw?
Yeah, well, so when you look at the predictions that the algorithm makes, so if you look at, for example, the predictions from right now that the algorithm makes, some of them, a lot of them, I would say, are what I would call adjacent to known thermoelectrics. So these are things that, maybe are fairly likely that someone would find in the next few years anyway, even if it weren't for the algorithm. Mm-hmm. But I will say that, 5 years, like a 5-year acceleration is actually a pretty big deal. The typical timescale for kind of materials development is usually quoted around 20 years based on an article that was published in the 90s. Mm-hmm. And so cutting 5 years off of that is actually would be considered a major milestone, I would say. Absolutely. And so, yeah, so, so a lot of the predictions are, I would say, chemically adjacent to some of the known thermoelectrics and probably would be found in a few years regardless. But then there are also a bunch of predictions in there that would look strange, I would say, to someone who is interested in thermoelectric materials. And those materials, I think, are more the wild card because, they could be strange and they could just be incorrect. But they could also be strange and they could also be correct at the same time, in which case it would be very interesting because it's finding really unconventional materials that may not have been studied if it weren't for the algorithm, even after 10 years or even after 20 years. Mm-hmm. So it will really require someone to really, the only way to really test that out is to do experimental tests on some of them and see whether they pan out or not. But yeah, there's a mix of things that maybe would have been found in the next 5 years or so, and things that probably wouldn't be studied even after quite some time. But I would emphasize that even 5 years is actually considered to be a very big acceleration.
Mm-hmm. And is the testing that you're currently doing with your collaborators, is that focused on either end of the spectrum, or do you have folks looking kind of across the adjacent materials as well as the ones that are strange looking?
Yeah, so Unfortunately, we don't have any dedicated funding to pay experimentalists to just look at whatever materials we'd want them to look at. If we had that, yeah, if we had that, I think we would try to spread it out a little bit more and do kind of both. But because we're kind of working, these experimentalists that are collaborating with us, they're doing it essentially in their spare time. And so they typically will work on materials that are similar to things that they're already interested in. So things that are, more simple to make and things that are, kind of within their comfort zone of synthesis and characterization.
Got
So
it.
I would say that the couple that we're working on are more in the adjacent category than the wild and crazy category.
And is the predictions that the model is making, is it predicting structure in addition to components? For example, I'm thinking if you gave it a prompt like liquid or wet, and it came up with hydrogen and oxygen, that it's still missing the two in H2O and that configuration. Is it giving you that, or is it does it leave that bit to the imagination, so to speak?
Yeah, so it's giving you a full chemical composition. So it would give you the H2O, but it isn't giving you a structure. So it isn't telling you whether it's ice or water vapor, for example. And that is actually one of the big limitations of the study. In material science, one of the main things you study is how the arrangement of atoms, not just the chemical formula, but the arrangement of atoms affect properties. And so, for example, if you think of just carbon, carbon can exist as diamond, it can exist as graphite, or it could exist as like a nanotube. And in our model, all those carbons are the same carbon. And you could imagine that a more advanced embedding technique, so some of the context-sensitive embeddings, something like BERT, for example, might be able to distinguish between those carbons and provide different predictions for carbon that are synthesized or that have different types of structures within them. But within our Word-Tyvek model, where every carbon is the same, regardless of whether it's diamond or graphite, it's really just the chemical formula that's being used to make the prediction.
How is it coming up with the chemical formula for these different compounds?
Yeah, so that's actually another one of the limitations of the current approach, which is that the current approach can only rank chemical formulas that are observed in the abstract corpus for an application. So it's not inventing new chemical formulas. It's only taking the list of, tens of thousands of chemical formulas that it's detected and ranking them for a particular application.
So maybe we're talking about things that have thermoelectric properties. But the only reason why the model knows about this particular compound is because someone looked at it for something else at some other time.
Yeah, that's right. And so, one of the associations that it might make, for example, is that the algorithm has found that there's some overlap between compounds that are studied for photovoltaic applications and thermoelectric applications. So it might detect, for example, that there's a particular material that has been studied for photovoltaic applications. It might have some other keywords that it likes that are also associated with thermoelectrics, like chalcogenide or Heusler, for example, and decide that, here's something that has a lot of keywords that tend to associate with thermoelectrics but hasn't been studied before. So it's making those sorts of connections across the literature.
Mm-hmm. And so in order to train this embedding and build out this model, did were there things that you needed to kind of invent or innovate on beyond kind of Word-Tyvek as, it's becoming increasingly common, or was it a fairly straightforward application of Word-Tyvek to get to this?
Yeah, so, unfortunately, one of the barriers to doing scientific literature mining is that the data sets are not easily available.
Is the scientific literature itself?
Yeah, well, because all the abstracts and everything are under publisher agreements. And so, for example, we couldn't publish the data set of abstracts to share with everybody. We were legally not allowed to. And so what that implies is that anytime you do a study like this, you have to spend a lot of time in collecting the data and pre-processing the data and tokenization and all that stuff.
Mm-hmm.
So
and just to be clear, so your entire model is based only on abstracts or the full content of the articles?
Yeah, so what we showed in the paper was based only on abstracts, so
okay.
no full text there. And so in terms of whether it was just straight to Word2Vec or, something more custom, I would say all the customization came from the actual pre-processing of the data. So things like being able to detect chemical formulas and doing the tokenization properly, things like that. And being able to collect the data in the first place was a bit of an effort as well. And so because we had to spend a lot of time in that process, we didn't have a lot of time to actually work with the algorithm itself. We also spent a lot of time verifying whether the results were correct or not. So that's where most of our time went. So this was, I would say, a pretty straightforward application of Word2Vec. We did test against Glove. We did do some hyperparameter optimization, things like that. But it's definitely, I wouldn't say we made any conceptual leaps in NLP during the course of this study.
Sure, yeah, and that question was not at all to take away from what you did, but rather see if there was any hidden element that would be worth exploring further. I think what I'm hearing is very consistent with what I hear speaking with lots of folks is actually applying this stuff involves a ton of work setting up the data pipelines and in your case even getting access to the data.
Yeah, and in some sense, it's kind of interesting to know that even one of the simplest word embedding algorithms is capable of giving good results on this problem. And so it really kind of begs the question: well, what if we were to use more advanced techniques on this problem? What if we were to expand the data set to the full text? What more might be possible? I mean, if we're already seeing such good results using simple techniques, there could be a lot of opportunity here if we were to actually spend even more time to do this a little bit more carefully.
And so if you were to kind of, think about the opportunities that are ahead of you, kind of in this direction, how do you rank them? What are the things you're most excited about kind of building on, and where do you think the true opportunities lie?
Yeah, so actually, a lot of the motivation for this study was not necessarily to make predictive models, but just to really improve the process of information retrieval from the scientific literature. And I think there's really a lot of opportunity in going from this mechanism where scientists are just browsing articles one by one for relevant information to really using algorithms to getting the information that they need just in time from the research literature. So to kind of use an example or an analogy, back in the early days of the web, if you wanted to look up Planck's constant, you would have to find a bunch of science websites, browse through them, and see whether one of them had the value that you wanted. Today, you just type Planck's constant into Google and it just immediately returns the answer. You don't have to browse anything. And so I think there's a lot of opportunity just in information retrieval from these very scientific abstracts. In terms of the actual predictive models and hypothesis generation, we already touched upon the ability to make predictions on materials that are not in the data set already. So how can we actually invent word embeddings for hypothetical chemical compositions? That's an area that we're looking into right now. We're also interested, as we spoke about before, of these more context-sensitive embeddings and these more advanced methods that might help us distinguish between terms and materials that aren't really the same, but are the same currently in our Word2Vec model. So these are all areas that I think we will be touching upon in the future.
What haven't I asked you about this research that would be worth exploring?
Yeah, I think one thing that I just want to mention is that somewhat ironically, this paper is behind a paywall, but but the publisher, so the publisher Springer Nature, they've actually made the full text available to read for free on ResearchGate. So hopefully we can put a link to that in the show notes so that people that want to read the paper but don't necessarily have access to it can actually legally read the paper. So I think that's one of the main things that I just wanted to mention about this.
Okay, that's awesome, and we will definitely include that link in the show notes. Anubhav, thank you so much for, well, A, listening to the podcast, and B, jumping on to share a bit of what you're working on with all of us. Thanks so much.
Yeah, it's been a pleasure. Thanks.
All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. Make sure you head over to twimlcon.com to learn more about the TWIMLCon AI Platforms Conference. As always, thanks so much for listening, and catch you next time.